Everyone, let me welcome you to the 27th session on ECT 204 signals and systems. In this video, we see the effect in the frequency domain effects of sampling. Okay, sampling actually we taught in many passes. At first, I told you about sampling of continuous time signals to produce discrete signals. Then, at that point, I told you about the sampling theorem, a brief introduction to the reconstruction formula, the Whittaker reconstruction formula. Then you do not know about convolution. So the Whittaker formula and the reconstruction I told you just after convolution, after discussing convolution. Now then also you didn't know about spectrum. Now that we have understood the Laplace transform and the Fourier transform, let us see the what happens to the spectrum of the signal on sampling. It's a very short speech. The contents of today's session are your learning outcomes, then sampling by multiplication by impulse train, and the summary of understanding. Here in this video, you will understand the effect of sampling on the spectra of signals. The sampling is accomplished by multiplying the analog signal xat by s in a train of impulses st. That is, the sampled signal xst is equal to xat. This is your analog signal or continuous time signal to be sampled. That times st, that's a sequence of impulses. So this is nothing but a summation from minus infinity to infinity xat into delta t minus nts, because this st is actually a sequence of impulses that can be written as sigma n from minus infinity to infinity delta t minus nts. Ts is your sampling time or sampling interval, which is 1 by fs. So this xat is multiplied by delta t minus nts summed over n from minus infinity to infinity. Now this analog signal, consider that this analog signal is an analogy signal. Xat has a Fourier transform, say xaf. So the Fourier transform and the Fourier transform of the impulse train, we saw that we can find the impulse response of certain periodic signals. So there we discussed the impulse train. We found out that the Fourier transform of the impulse train st is s of f, that is 1 by ts, k from minus infinity to infinity delta f minus k by ts, because the Fourier transform of an impulse train is another impulse train in the frequency domain with a frequency spacing of 1 by ts, and the magnitude is divided by ts. So sf is 1 by ts, k from minus infinity to infinity delta f minus k by ts. So when I multiply, the spectrum of the here it's a time domain multiplication. xst is obtained by multiplying xat by st. So in the frequency domain it appears as a convolution between xs and fs. So effectively xas or xif, I'm talking in the frequency domain, xif, that will be convolved with this sequence of impulses. So a convolution of a signal with an impulse is results in the same signal. So what happens is xsf, that is equal to xif convolution s of f, that is xif convolved with 1 by ts, k from minus infinity to infinity delta f minus k by ts. Okay, this is equivalent to 1 by ts, k from minus infinity to infinity, xa into f minus k by ts. The above equation, this means that the spectrum of the sample signal is a periodic repetition of the spectrum of the analog signal. Okay, xif is repeatedly placed from minus infinity to infinity. So that looks like this. Consider that, assume that this is the spectrum of my original signal, say a triangular kind of shape. It is from minus fm to fm, say with a magnitude of 1. It can be any arbitrary shape. I assumed a triangular shape here for the sake of simplicity. So xf with fs greater than 2fm, that is if it is above Nyquist sampling rate, or I may increase the size a little. So here this is my xif, that is a triangular shaped from minus fm to fm with a peak value of 1. So if xf is with what happens to the spectrum of the sampled signal with the sampling rate is greater than 2 fm, it is greater than the Nyquist rate, what will happen? This XSF will be what? It will be a repetitive placement of original XIF at every 1 by Ts. So here, this is my original signal. This is my XIF, and this is a replica placed at 1 by Ts. This is my sampling rate 1 by F 1 by Ts. Fs is 1 by Ts. This is in the negative direction. So this spectra will be repeated placement of the original spectra from minus infinity to plus infinity. So here here you can see that this is my original spectrum minus Fm to Fm, and this is the next one coming here, and this Fs is 2Fm. So you can see that I can conveniently place a filter of bandwidth B here. Okay, I can place an ideal low pass filter with whose impulse response is sine 2 pi bt by 2 pi bt, which is a sinc function which appears in the frequency domain as a rectangular signal. So this rectangular signal spans from minus b to plus b. Okay, since this b is greater than Fm, and we know that there is a band here, there is a, I can conveniently place, there is a separation between the two spectra here. I can place a filter conveniently in this above Fm and less than Fs minus Fm. So I can conveniently filter this signal out. I can perfectly reconstruct my original signal. Now what happens is Fs is 2Fm, that is the exactly at Nyquist rate if I sample. So here you can see that the spectra are placed very close, that is Fs is 2Fm, this is Fm, this is another Fm, so Fs is 2Fm. So here also I can conveniently place a filter, no problem. But in the practical difficulty, I told you in the previous classes that that is I can always sample at Fs equal to 2Fm and I can reconstruct the signal. But if the sampling happens to be at the zero crossings, then I cannot reconstruct the signal. That is why I always take Fs is greater than 2Fm rather than Fs equal to 2Fm. But in some cases, if the sampling does not happen at zero crossings, I can reconstruct the signal. So here also I can place a filter. Here this B is equal to Fm. Okay, here B is equal to Fm. So I can place a filter and reconstruct the signal. Now what happens is Fs is less than 2Fm, then what happens is undersampling happens. Here this is my original signal, original spectrum. Here is a replica of placed at replica placed at Fs that is less than 2Fm. So what happens is there is some overlap here. Here there is an overlap, here there is an overlap. So here I cannot easily place a filter and reconstruct the signal. So some kind of distortion will occur at these frequencies. These frequencies will be distorted. But you know, for in certain applications this is not a problem, like video signal processing, etc. It may not be a problem. There you use go for sub-Nyquist sampling. But for speech signals and all, we sample at a frequency greater than 2Fm, sometimes 8 times the analog frequency. Observe that when Fs is less than 2Fm, there is overlapping of spectra and reconstruction filter is not possible. Now, when you come to the end, you here in this video, you understood the effect of sampling on the spectra of signals. And that is the end of this presentation. I thank you all.